Hello and welcome. We are looking at our organic compounds, and this is a second video to look at organic compounds. And if you remember, we said that organic compounds were the basis of all living things. They contain carbon, and the examples that we wanted to know about were the alcohols, carboxylic acids and esters. We have done the alcohols. We are now going to look at another group of organic compounds called the carboxylic acids, and that's what this video is all about. Now, the first thing is for carboxylic acids, they have a functional group as well. For our alcohols it was OH, but the functional group for our carboxylic acids is our COOH group, and this is often written like this, but it can be shown in the structural way as I've shown on the right hand side here. Sometimes you might see in a textbook as written like this, where the O is double bonded at an angle and the OH down there is at an angle as well, but it's the same thing. The spec writes it like this, so this is likely how you'll see it if you see it in the exam. Now we need to remember three particular carboxylic acids, and those are methanoic acid, ethanoic acid and propanoic acid. And just as a little hook to help you perhaps remember these names, you remember the alcohols were methanol, ethanol and propanol. Well, these follow a similar pattern in their names, in that we've got methanoic acid, ethanoic acid and propanoic acid. You'll also remember the alkanes. We had methane, ethane and propane in that order, and so that might just help you just to remember what order they go in, or actually the names of the different carboxylic acids. I'm going to remove the alcohols here because I don't want it to confuse matters. Okay, so the first thing is then, how do we draw the structural formula for methanoic acid? Well, this is quite a simple one. We have a little H sitting there by itself, but it can't be a carboxylic acid without its functional group, and here is our functional group. So all we have is, for methanoic acid, we have our little H with the functional group attached, C double bonded to oxygen, and our ONH bonded like that. How would we write that as the formula? Quite simple. You can probably look at that and guess. If we know the functional group is COOH and all we're doing is attaching it to an H, then the formula is HCOOH. For ethanoic acid, very slightly more complicated, but not hugely. We have our H there, but we have a CH2 in the middle. We just add our functional group there, and there we have the structure of ethanoic acid. If we were to try and write this out as a formula, again you could try and guess. We have a CH2, not a CH2 there now, we have a CH3, and we have our functional group. So how would that look? It looks like this, CH3. You can see that the CH3 there links to this, and our COOH is our functional group, is that bit there. Our propanoic acid, we have now a CH3, we have a CH2, but we don't have our functional group, so we can just add that on. There it is, and there we have propanoic acid. And what would be the formula for that? Well, we have a CH3 over here, a CH2 in the middle, and our functional group, which is COOH, so that would just simply be CH3, CH2, oops, little mistake, CH3, CH2, COOH. Okay, so we are supposed to be familiar with these three. We are supposed to know how they look in a structural formula and in a written formula like this. So this is probably worth going over one or two more times. This does look quite complicated, but when you break it down like we just did, that might make it easier for you to remember. Now, there are a couple of features you need to remember about the carboxylic acids, and they are as follows. We have that they dissolve in water to produce acidic solutions. Remember, our alcohols produce neutral solutions, but our carboxylic acids produce acidic solutions, and if you think about it, actually makes sense. Carboxylic acid makes acidic solutions. Remember then also that they can dissolve in water. They react with carbonates to produce carbon dioxide. Now, you don't need to remember any particular formulae for this. You certainly won't be asked to balance a formula that is a reaction between a carboxylic acid and a carbonate, but you might be shown one, and one looks a bit like this. So here's a reaction of ethanoic acid with sodium carbonate. So sodium carbonate is our carbonate. We get sodium ethanoate, our water, and carbon dioxide at the end there. So if we react our carboxylic acids with carbonates, we're going to produce, we know for a fact, something, but also carbon dioxide. The last one here is they react with alcohols. We've looked at alcohols already, plus an acid catalyst, and they make these things called esters. We're going to look at esters in another video. The last little thing here is for the higher tier only, so I've done it in red, and it says here that they do not ionize completely in water, so they make weak acids, and they have aqueous solutions. The aqueous solutions of carboxylic acids have a higher pH than aqueous solutions of strong acids with the same concentration. Now there's quite a lot of information in there in two quite short sentences, and we need to understand exactly what that means. Remember, it's for the higher tier, so if you're doing the higher tier, we're going to look at that next. So here we have those two sentences written down just as a reference, but we're going to look at two acids. We're going to look at hydrochloric acid, and we're going to look at ethanoic acid. Hydrochloric acid is often referred to as a strong acid, and ethanoic acid is often referred to as a weak acid. But if we look at two concentrations of these two acids, they are exactly the same here. We've got a 0.1 mole per decimeter cubed solution of hydrochloric acid and a 0.1 mole per decimeter cubed of ethanoic acid. Now the problem is, or the issue here is, here we're saying it's a strong acid and here we're saying it's a weak acid, even though they are both the same concentration. This one over here, hydrochloric acid, will produce a pH of around about 1.0, and this will produce a pH of 2.9. So here we said aqueous solutions of carboxylic acids have a higher pH. So here's our higher pH. That means it's less acidic. Remember, our pH scale goes from 7 down to 1, and 1 is the strongest acid, and 6 is the weakest acid. So here we have a weaker acid with a higher pH number, even though the two concentrations are the same. Why does this happen? Well, we need to look at what happens when we dissolve these two in water. So here's our hydrogen chloride being dissolved in water to make hydrochloric acid. What we say is that it ionizes, it splits up into our hydrogen ions and chloride ions. Now it's these hydrogen ions that are very important, because an acid is dependent upon the number of hydrogen ions there are in a solution. So we've got a large concentration of hydrogen ions in a solution, we are going to have a more acidic solution with a lower pH than if we had fewer of those. So hydrogen chloride will ionize into H plus and Cl minus, whereas for our ethanoic acid, here's our formula for our ethanoic acid, that will actually ionize into CH3COO with a minus and our H plus. Now this is not something that you have to memorize, but this helps to explain why we have a weaker acid. Now that's all fine, we have our hydrogen over here, but this is the key to why we have a weaker acid with ethanoic acid. With hydrogen chloride, it will dissociate, or ionize, sorry, into hydrogen ions and chloride ions, but the key with our ethanoic acid is that this process is reversible. So while we can go from ethanoic acid to our CH3COOH plus our hydrogen ions, this is reversible. So we're going to get movement in the reverse direction as well as movement in the forward direction. So this happens and it will reach equilibrium, and when it reaches equilibrium, that means the same number of molecules of CH3COOH or ethanoic acid are ionizing to make these two. We also have these two reacting to make our ethanoic acid. So we reach equilibrium, and that means we won't have as high a hydrogen ion concentration in our solution as we would with hydrochloric acid. So if we have a lower solution or a lower concentration of hydrogen ions, we are going to have a weaker acid, because the acid depends on the number of hydrogen ions there are in the solution. So to summarize that, we could say that the ethanoic acid ionizes, but only some of it ionizes. The reason is the process of ionization in solution is reversible, and therefore we have a lower concentration of hydrogen ions in solution, and I've just put that as aqueous. Aqueous, AQ, means in solution. So we have a lower concentration of hydrogen ions in solution, therefore we have a weaker acid for the same concentration of our solution. Now that means that reactions of ethanoic acid will be slower for the same concentration than hydrochloric acid, simply because of this reason here. So that's quite tricky there. It's probably worth going over again if you're not quite sure, but this is a summary of the reason why the same concentration of ethanoic acid will produce a weaker acid than something that is a strong acid. Okay, so this is carboxylic acids more or less covered for the exam. That's me done for this video. Thank you for watching, and I'll see you again soon.